Okay. The floor is yours, Buffy.
Okay, thank you. Thank you so much. Hello, everyone. I think most of you are in the Netherlands. I see you from the US. I'm joining here from India with my friend. I haven't named my friend yet, but yeah, thank you again for inviting me to this talk. I didn't expect when I was creating the project, sitting in my room, just doing a bunch of stuff. I didn't expect anybody to even come across my project, yet alone being invited to this 10th anniversary. So thank you so much. So yeah, let me start my presentation. But before that, I'll introduce myself as well. Is my screen visible?
It's black.
It's coming, yeah.
Yeah, there it is.
Okay. So I named this face stitching, but technically you can replace this with this first word with anything else. You'll see that in a second. So yeah, about me, I am currently a student. I'm doing my integrated masters at NIT Surat in math and computing. And I my mind is full of ideas. I constantly keep working on some of the other thing. It could be building like physical stuff, or mostly it's on the computer. I program and I design as well, but mostly it's about math animations. So I like to usually animators do it using a software, right? I take a different approach. I create animations using math. So I'll quickly go over my channel as well. Yeah, so this is my channel, and all of the things that you see over here are completely made using math. So yeah, I do that, and yeah, some of the domains I'm currently researching and delving into is numerical analysis, game theory, machine learning, and also category theory. So it's a big mix of pure math and a bit of applied math and theoretical CS. So I'm juggling between multiple domains. So that's about me. And in today's talk, are you able to see the whole screen, or is the left side
No, it's
blocked?
okay.
Okay, yes. So the goal of today's talk is to convert any given image into an embroidery using a single line. So here you might see this Turtlestitch logo, right? But if you zoom in, it's just a single line. So how cool is that? So this is our goal. We want to compute this path, a single line path, as well as stitch it. And today I'll cover all the theoretical process as well as what we need to generate this. So I was inspired uh, when I saw this competition where you have to turn this Mona Lisa image into this art and you can win $1,000. So many people have attempted this. Basically, you have to get this image with a single line, the same theme. And this was started by Robert Bosch. He has his book called Opt Art, which means optimization art, where he creates art with optimization. So let me show you his work. And when I saw this competition, I was inspired to create that, but in the domain of stitching. So maybe you can finally print it on your shirt, things like that. So if you search Opt Art by Bosch, you'll find these things. So he has created, this is made with dominoes, and he computed this using optimizations. Similarly, you also have this Mona Lisa, similar theme basically. He generates different images with constraints. So the constraint could be generating an image using dominoes, generating using a single line, and this, yeah, he's Bosch. And in the background, you see this beautiful art. It's basically a knot, but on the macro scale, it's a knot. But if you look deep, it's just a single line. So if a single line is drawn, you can tear it apart, pull it, and it's not a knot anymore. So the significance of this piece in the background is basically he's making a knot without a knot. So that's the significance of this art in the background. So yeah, that's about Bosch. I was inspired by this challenge, but I wanted to compute it. He has mentioned how it's done. It down compute and make a interface for it. So that was the inspiration. So the first step is it's called to a list of points. So you can do this in many. Let me go to Paint and show some of the ways you can do. So suppose you have an image, you can first turn it into grayscale or combine the RGB into any form. Maybe 30% of red, 70% of green, or 30%, 60%, 10%. Choose any combination, convert RGB into grayscale. After you do that, you have a bunch of pixels, right? Let me draw some pixels. For now, I'll just draw a 4 by 4. Yeah, this is enough. So every pixel will have a number between 0 and 1. So this is your grayscale image. And what you can do for there are three types. I am talking about regular stippling, where you have these numbers. Let me write out some numbers. So these numbers could be anywhere between 0 and 1. So yeah, all of these are filled with some numbers. And what you can do is convert this grid into a probability distribution where you have to calculate the total and then divide each of these numbers by the total. So finally, you get a copy of this image. This is the first step. I'm basically trying to convert this image into a stippling, which is a bunch of points. So I take this, I divide each of these numbers by a total, the total of all these numbers. So finally, what you get is you get n squared over here, and all of them sum up to 1. And all of those numbers aren't equal, right? So you get a probability distribution. After this, what you do is you have a random number generator. So in a stippling, you can choose the number of points you want. This is up to you. So suppose I want, let's say 10,000 points. So what I do, I use a random number generator, use this probability distribution and throw a dart. It's called dart throwing algorithm. It sounds fancy, but it's just using this probability distribution and throwing one dart at a time. So the first dart probably lands over here. The second dart probably over here. It could repeat as well. Third dart maybe lands at the same place. Fourth dart, and then you do until you get 10K. So you get 10K points or less on a grid. So this is your final stippling. So if you do that, you'll get an image like this. So that's regular stippling. Are you guys bored or should I continue with the other two? They're basically different forms of stippling, the same thing, basically converting this image into these bunch of points. Should I continue the second one? Okay. So the problem what happens with this regular stippling is sometimes if you have an image with a background like this, so this background is not white, it's a bit creamish, right? So when you convert that to grayscale, all of these values probably would be 1.2, 1.2, 1.2, and so on. So the final stippling that you get would have this equally dense points over here where the shade is same, and the places where the shade is darker, you see uh, points with greater density. So that's the outcome when you do the stippling. And that's what we want for this first step. But the thing is, I don't see any features over here. So here you see eyes, lips, nose, my shirt, but here you don't see that very much with regular stippling. So with the second algorithm, this is mentioned as in his book, OptArt, where on top of this you do an extra iteration. You generate after, let's say you generate 10K points, so all of it is done. You reach the stage. After you reach the stage, what you do is you generate an extra point. So this extra point is called a beam, and this point is generated using the same probability distribution as the other 10K points. And once you generate this beam, you find the point that's closest to this beam. So over here, uh, this point is closest, right? You find this point, and then you move this point closer to this beam, and then you do this over and over again. So the reason you're doing this is uh, the beam itself is generated by the probability distribution as before, but then again you're using those beams to change the original positions. So by that, after you see this, you'll avoid a lot of extra points, and you'll final positions where they land, you'll be able to see more features. It's in his book as well. I'll show you the example he has. Yeah. So here he has this input image and he does regular stippling, and you get this. It's fine. It's all, but you can do better, right? Over here, these empty areas, you can have equally spaced dots. So after doing this beam method, you can do it any number of times. So you get this image. And over here, you see that in the background, the dots are equally spaced, and inside as well. And inside you have dots with higher density. So that's the significance of this beam, uh, between stacked beam algorithm. And you do this any number of times. So keep counting the number of hyperparameters you have, because these are valid. So the five things that you're doing, all of these you'll have to take into account. Basically, one thing is the number of stippling points. Second thing is number of iterations you do on top of this. So for now we have two. So yeah, this is the second one. The third is Voronoi stippling. This is another algorithm to convert this image into a bunch of points. After doing stippling, we apply an algorithm called TSP, traveling salesman problem, to find the lines. So in this, you don't only see points, you see a path, right? So to get this path, you just have to take these points, apply traveling salesman problem. I'll explain what that is, and you'll be able to find the path between that connects these dots. So TSP is traveling salesman problem. Imagine you're a traveler. You have to go to different cities and visit all of the ones and then get, and you have distances between these cities, and you're trying to find the path, shortest path to those cities, and you want to come back to this. So it's called a Hamiltonian path. So it has various applications. So here you see map of USA. You have all these cities, and this blue path is the path that minimizes the distance. So either the distance can be arbitrary, like over here, where you can have a matrix defining what distances are between each of these nodes, or you can have geographical distance, Euclidean distance, where you just use Pythagoras theorem between adjacent nodes to find the distance. So we'll be going with this, and we'll be using that uh, on top of this to find the path. So yeah, first step is stippling. After that, you run TSP, and then finally you'll get an image like this. So, but the problem with the TSP, traveling salesman problem, is that it's NP hard, which means for small number of points, let's say 5, 6, it can be computed very easily. You can write a Python script let it run for 5 minutes, and after 5 minutes, you can get the result, the path. So over here, the path would probably be 1 2 3 4 1 3 4 4 2 any question. So you have n square uh, combinations when you're doing brute force. So you can come up with a bunch of paths, calculate the total distance for each of the path, and then select the path which has shortest distance. So if you do this, uh, the number grows really large, very good. So let's say you have only 20 cities. 20 factorial is 2 times the power of 18. It's too long to compute that path. So how you apply TSP on the set of, because the number of points I'm taking is 10k. Imagine the factorial, what the factorial of 10k would be. It would be too huge. Calculator says undefined, but it's probably a number. Yeah. So the solution to this, is you can't run TSP on so many points. And first of all, suppose you just have 10 points. How will you compute the TSP for that bunch of points? You can either use Python, which is fine, but it's not optimized. So there's this solver called Concord. I'll open it up. You can install it on Windows as well, where he can define what the cities are, either manually or uh, using a file. You can define it in a file and you can import it. So let me draw a bunch of points. So these are some cities, and I want to compute the shortest path, the TSP path for this. So I can just go to solve. Yeah, I don't know, it doesn't allow me to click while I'm presenting, but after I go to solve and I uh, enter some parameters and then click on solve, it will compute the path. I don't know. Yeah. So you can do this at 10 points, 15 points, but you can't go above 15. It takes too much time for TSP. So there's a better thing you can do. You don't have to depend on the best path. You can choose a suboptimal. So KHS, Lin Kernighan heuristic, which is another algorithm that's solving for the same thing, but it's not NP hard. So it takes computationally less time, as well as it's much better. But you'll get a suboptimal path. You'll not get the best solution. So this LKH can also be run on this Concord. You can see over here, right? L. So you can run this algorithm as well, and it takes very less time, even for 10,000 points. So that's what we'll do. We'll first building and we'll not do TSP on top of it. Instead, we'll go for this heuristic algorithm. After we pass, we can just compute. It's fine. But finally, we want a .bst file in order to stitch it. When I first explored this, I didn't even know what Turtlestitch was. I searched how to generate .bst and then I came across Turtlestitch. So I had gone to that website.
Is the connected still on?
Okay, so you can
Oh, yes.
let it load and I'll show it to you. So on Turtles, you can write some code and then say export as GST. So that's what I've done. I compared the points, the path between those points, and then I imported the data to Turtlestitch. That was a test. You can do it store in .csv, and then I imported it to Turtlestitch, small code, and then exported as .dst. Huge process, and it's very manual. So that's method one. You can use a Concord solver create the .csv, import it to Turtlestitch, and export it as a .dst from Turtlestitch. So that's what I did with this project. This is my face upside down, by the way, because of how the coordinate is computed. It's loading. That's method one. Method two is all of these processes I simplified into a Python pipeline where I just maybe generating the DST file also doesn't require Turtlestitch. You can use some pipelines and get that done. The part was I wanted to calculate the LPH for the path, right? That also can be done using Python. So these two steps I brought it in Python, not PSP because it takes a lot of time even in Python. So string also can be different. So these three can be done entirely on Python. So you just have to put your image, run the whole pipeline, and then you'll get the .dst file. This also requires a lot of effort because you have to comparatively better than first method, but you have to run them step by step. And finally, I try to again merge these Python steps, Python files into one, make a website, which I showed in the beginning. Doesn't have the best of design though, but you can choose the file, upload it, and it takes like 2 minutes. I can show it. If you guys have any pictures that you want to try, you can maybe send some pictures to maybe mail and you can test it. So you can choose the file, upload, calculate the route, and then download the file all in. Let's see. So in this, what I did was I just had my CSV file on this window. And
Nice.
so in the CSV, the way I figured this out was I just defined a bunch of numbers and I said export from this. And what got exported was a .csv file, and all the numbers were stored in a single row. So to export the X coordinate, Y coordinate, and the path, I had three CSV files, stored it like this in a .csv. Here you see bts.x.csv, and then you just drag this to Turtlestitch, and then you get all of this. So you don't have to enter this manually. And then you can have a for loop, go over each of these, get the X and Y, and this is the index. So I have three things. The path. So the path has indices. It has something like 1, 7. You have main list of points, and from those list of points, to index it, to define a path, I have this path variable. So I store this index, and then I get the position in that array, and then I just say go to this X coordinate and Y coordinate, and after that you get this beautiful image. And because of the way the X and Y are defined, it comes up upside down, but you can make this into -y to flip it. Is there a way I can type as well instead of dragging? Does this let me type?
The sound quality is not absolutely perfect. It's good that we record it so that we can look at it again in detail. But as I understood, you asked us to upload an image. Is that correct? Or do you have an image? I mean, I have also set up
Yeah.
the embroidery machine here. So if I mean, if you can proceed something, I could also just embroider something that you processed on Turtlestitch. I think this is a solution for now. Is that okay?
Yeah, I mean this could be done because I have this ready.
Yeah.
Or even otherwise, if anybody wants to have their face, any picture, they can send it over so that we can try.
Does
But
anybody
for now,
have
I'll send this file. Is it fine?
The webcam. Did he say this? No,
No,
I don't know. But
maybe
we
we
can
can
try.
use that.
Maybe.
Bhavik, perhaps you can take a screenshot from the webcam and use that.
Or is a screenshot? Is that a good quality? A screenshot? Maybe Cynthia, do you want to come?
Yeah,
We
it
make
looks good.
a photo from you, and we can proceed. You're a great person to make a photo.
Wait, let me take a picture as well.
Let's try. Yes, it's anyway good for energy. Let's try. But I don't know who can make a screenshot now. Actually, can somebody make it?
Bhavik
Or
should do it.
Bhavik, can you make a screenshot of Cynthia?
I just sent you a
Yeah,
picture
sure.
of a flower.
Elaine, where did you send it to?
It's in the chat, the Zoom chat.
Okay, whatever. We try.
Wait, I sent the wrong image. Let me take a screenshot once again.
So that everybody here sees
Okay, I
what's
got it.
going on. Elaine sent this picture of flowers.
I mean, not every picture works, I'm sure.
Yeah.
So maybe
You need some context, probably.
Yeah, exactly. I think so. The best that you. So, Bhavik, maybe you take just
Yeah.
a big picture that you think works good. I think that's easier than
Yeah, sure.
us taking a picture. Thank you.
Yeah, I just sent it over in the chat.
Okay, cool.
Okay.
Okay. Do you get it?
Yes, no, go.
Yeah, I've taken a few pictures. I
I
can
would
send them.
prefer the DST file, to be honest. Not the picture.
Just a second.
We received your screenshot. Do you want us to do anything with it?
No, she asked me to send those pictures, right?
That's good.
Are
Yeah,
they?
that's fine. Barbie, you know what I
Yeah.
did? I have opened your website. Look, I have opened your website. Where is it
Okay.
like this? And I will simply take this picture from your project that you generated to a DST file, and I take the DST file, plug
Yeah,
it
sure.
into the machine, and embroidery. I think that's the best thing.
Yeah, that would
Okay,
be
then I
nice.
do that. Yeah. Okay.
Yeah,
Here we go.
sure.
Shall we then also change to Elaine as a presenter?
Yes, but maybe wait 2 or 3 minutes so that we have
Okay.
a finish of the session. So
Maybe if you can point the camera to the stitching machine, I can turn on my screen recording and record that as well. Yeah.
Yeah, but it's a little bit because I hope my computer can do it because it's so weak.
Okay.
Zoom to fit. See. I usually have a mouse here. So actually, I have my computer here, and you see how it is proceeding. Yeah.
Yeah.
This is good. Thank you. And can I zoom out? So I will make the turbo mode. Okay, so this is the picture is generating. And I switch on the machine, and I will save the DST file.
By the way, is there a different way than using a USB to transfer the DST file?
Can you say it again?
Yes, if there's another way apart from the USB to transfer the file.
On different machines, you have different possibilities, yes. I
Okay.
will put it in here because there's nothing in. This depends on the machine.
In the meantime, anybody has a question for Buffy?
If we
Yeah, I would
want to
love to take
convert
questions.
our own,
Oh. Yeah?
do you have a ready-made website, or do we follow the steps with Concord and then DSP?
Yeah, I post the website, so I'll share it to your own laptop and following the 2 to 3 steps can do it easy.
Could you repeat that?
You still have one?
What? Do you see one?
Yeah.
Okay. Thank you.
Hello. Yeah, what I was saying was, I can put out the code on GitHub and you can just do it on your laptop, do 2 to 3 steps, and you can generate it for yourself.
Okay.
But the website is not hosted yet. Did I answer your question?
Yes.
Yes, there was a question. So ask.
There was a question I didn't know. So I'm going to embroider now, okay?
Yeah.
Let's try. Okay. I hope I don't have anybody has a scissors. No.
Scissors.
Scissors.